Of all the three different kinds of rocks, I think metamorphic rocks have to be the least understood of all, and mainly because we've never seen any of these rocks form in any fashion. No part of their formation can be seen. We're going to see, for we're done here, that this process of metamorphism goes on only at great depth within the Earth, far from any view. And so the problem with studying metamorphic rocks and really understanding how they form is that the only thing we can see is what we see at the surface. Then we have to surmise what it is that caused that change to take place. A definition, for example. The definition of a metamorphic rock is any rock that forms from a previously existing rock as the result of heat, pressure, and chemically active fluids. Well, the fact of the matter is those conditions, high temperature, high pressure, and those chemically active fluids just don't exist on Earth anywhere except at great depth. As opposed to let's say igneous rocks. Now we can't see obviously a big mass of granite being emplaced into the edge of the continental crust, but we can see other kinds of igneous rocks forming. Certainly you can go to the Big Island of Hawaii today and you can see molten rock spewing out of the Pu'u'o'o vent and pouring down the hill as a river of basaltic lava flowing toward the southern shore. You can see it splitting off here and there and solidifying and making new lava, new hard basaltic lava. So we can see that, at least that part of the igneous rocks we can see. And granted, we just got done talking about sedimentary rocks. And in sedimentary rocks, granted, we cannot see those processes of lithification. Again, the compaction and the cementation we talked about, those things only happen after burial. But at least we can see everything else. We can see the materials accumulating on the Earth's surface, whether it's on land, whether it's on the ocean bottom. We can see the materials being created. So we have a pretty good feeling for at least what we're working with. But the metamorphic rocks aren't that way. We simply have to take what we see at the surface and then try to figure out, well, how did they get that way? Now, a couple of other just general comments about metamorphism in general. Usually, and we're going to talk about three different kinds, but usually in metamorphism, there's no change in composition as you go from the original rock to the new metamorphic rock. Think of the process metamorphosis of a caterpillar to a butterfly. I'm not a biologist, but I don't think you've added anything in the process or taken anything away. You've taken the stuff of which the caterpillar is made and you've turned it into a butterfly. So the materials are the same, it's just that they are in different shape. And that's the way most of these metamorphic processes are. You take an original rock, whatever the mineralogy is and whatever the composition is, you turn it into a new set of minerals perhaps, but the composition is the same. So you really haven't changed anything, you see. Now, the other thing about metamorphism that I sort of want you to have a feeling for, what the change is all about. The change basically is the result of taking a rock that was created under one set of conditions of, let's say, temperature and pressure, then exposing it to a new set of temperature and pressure conditions. Now, here's the way to look at it. The original rock, let's say it's a sedimentary rock. The conditions of temperature and pressure were atmospheric temperature, atmospheric pressure. The minerals that you see in that rock, whether it's a sandstone or a shale or whatever, those are the minerals that are stable at atmospheric temperature and pressure. So the idea is that the minerals of which every rock is made basically are those minerals that are stable under the conditions under which it was formed. But now you're going to take this rock, let's say a shale, that formed under conditions of atmospheric temperature and pressure. You're going to bury it deep in the ground, perhaps probably in a zone of subduction. You're going to increase the temperature, you're going to increase the pressure, and all of a sudden, those minerals we're talking about, they're no longer stable anymore. So what do? Well, what you do is you change them into a new assemblage of minerals that are stable. For example, in the case of shale, it's mostly made of clay minerals and quartz. Well, if you increase the pressure and temperature on it, the clay minerals probably won't be stable because that was the mineral that was created at atmospheric temperature and pressure during weathering. So what is it going to do? Well, it may change into mica, which is a mineral that forms at higher temperatures and pressures. So that's the sort of the picture that I'd like you to have of what metamorphism is all about. Metamorphism is simply taking one mineral assemblage and changing it into a new mineral assemblage. A mineral assemblage that was stable under one set of conditions, now subjected to a new set of conditions of high temperature and pressure, and now it's just got to change into something that's once again stable. Now, the change in composition, one of the things we mentioned in the definition was chemically active fluids. Well, the chemically active fluid turns out to be water. And again, in my discussion up until now, I've indicated, and this is mostly the case, there is no change in composition. In other words, the elemental makeup of the original rock and the elemental makeup of the final metamorphic rock are the same, except when you start involving water. And we're going to see before we're done here that once you start involving water, remember you're talking about the universal solvent here. There's all kind of things dissolved in water. If you start involving water in this scenario, now you can add or subtract things from the original rock. Now you can end up with a rock with different composition and a different mineral assemblage. So there's sort of an overall picture of what metamorphism is all about. And again, you can see just by my descriptions that these are things that we suppose are happening down there, say within a zone of subduction or whatever, but we can't see down there, so we're absolutely not sure. Okay, now the various kinds of processes. These are actually pretty simple when you come to think of it. There are three kinds of processes: contact metamorphism, dynamothermal, and hydrothermal. Let's take up contact metamorphism first. This is the simplest picture. Let's say, for example, we have some kind of a mass of molten rock being ejected up toward the surface, and perhaps even into that layer of sedimentary rock at the surface, and then that's where it stops, and now it's going to start cooling off and eventually crystallize into some kind of a rock mass. Well, this is pretty hot, and next to it are the host rocks, which are not. Well, the contact between the molten rock and the host rock is literally just baked. It just baked, that's all there is to it. And so the contact of the host rock now, it starts to respond in the new conditions under which it's placed now, higher temperatures. And let's say, once again, I'm always going to use shale because it's the easy one to picture. Here we have a shale, for example, up against this molten rock. And now the shale says, well, the clay minerals are no longer stable, so it will change into mica. So now we have a zone right there at the point of contact with this molten mass cooling off that now has been metamorphosed. It's contact metamorphism. Now, obviously, the bigger this mass is, the more heat there is, the more penetration you can have back into the host rock, the greater that depth is going to be. In other words, the wider the band of metamorphism will be. So we call that the halo. There's a halo that forms around the intruding mass into the host rock where the rocks start to change. They're simply accommodating themselves to this new conditions of temperature and pressure, mainly in this case, temperature. Well, the other thing too is, let's say it's a very, very large mass, and so actually between the contact with the molten mass and into the host rock, there's a gradation of temperatures. The very hottest obviously right next, and as you go further and further away, still high temperature, but still dying off until finally somewhere out into the host rock is not affected by temperature at all. Well, as you might suspect, the kind of minerals then that could form within that halo would simply depend upon the amount of heat present. Perhaps right at the contact, the mineral assemblage would be different. Perhaps rather than mica, you might have chlorite. But then you step over, what's a little cooler, still hot, but now you have maybe mica. You step over a little further, and maybe you're into the unaltered zone. You're now back into the clay minerals. So the point is that when you look at these halos around these contacts, what you see are bands of different minerals representing the different ranges of heat to which the host rock was subjected. And the guys who study metamorphism, they look for certain minerals, which gives them a hint as to what those temperature levels are. In terms of mineralogy, the mineralogy of metamorphic rocks is very, very complicated. It's nowhere near as simple as that in igneous rocks, and certainly not as simple as in sedimentary rocks. And not being a metamorphic petrologist, my information is relatively limited to what I've seen in field trips and what I've studied. So anyway, there's the picture of contact metamorphism. A very, very simple thing, but note, in that case, heat is what dominated. Heat is the main factor involved. Now in the second one, dynamothermal metamorphism. The thermal, of course, you're talking heat again, and here's a good point. Heat is always involved. There is no metamorphic process that does not involve heat. So whether you're talking about contact metamorphism, dynamothermal, hydrothermal, heat is always a factor. But in this case, the dynamo refers to pressures now. We're going to talking about a combination of increased pressure and temperatures. Well, then just picture now, just based upon what we've learned in this course up until now, what environment do you think of when I picture high pressures and high temperatures? Of all the places we've talked about, you got to start thinking zones of subduction. I mean, we're talking here the biggest head-on collision in the world. There's no place on Earth that has the compressive forces that are developed like in those zones of subduction. So the amount of dynamic business, the pressures are enormous down there. Of course, the temperatures are too. As that plate descends down in further and further into the mantle, things are heating up all the time. And as a result, you have this combination now of dynamo-thermal metamorphism. Now, picture now how big this place is. A typical zone of subduction. Well, think about the western margin of South America. We're talking about a zone of subduction. Certainly it's thousands of miles long. What would be the three dimension? I expect down there, if you're talking about where's the influence of this zone of subduction, it certainly would be hundreds of miles wide and probably hundreds of miles deep. So we're talking about a vast mass of rock down there that's being converted as a result of dynamo-thermal metamorphism. But note once again, we've added nothing, we've taken nothing away. All we're going to do down there within this massive zone, we're simply going to take minerals that are already there. We're going to take the minerals that are in the basaltic oceanic crust that's being subducted. We're going to take the minerals in the gabbro, which is the same as basalt, of course, but that's being subducted. We're going to probably take some of the peridotite in the upper portion of the mantle. That's all part of the subduction zone. We may even take a little bit of the granite, which is the edge of the continent. So you see, we have an assemblage now of different minerals that we can use to convert into other minerals. But the point is, all we're going to do is simply take what's there under the new conditions and turn them into a new assemblage. We've added nothing, we've taken nothing away. Now again, going back to the size of this thing, how do we know what went on at all? Well, think about, again, two continents colliding. That would be the ultimate now in a head-on collision. Let's say two continents collided. Millions and millions and millions of years later, these two collision places come to the surface and now we're exposed. For example, the collision of the continents that created Pangaea. That created the Appalachians. That all was going on somewhere down in that collision zone between the two continents that ended up making the Appalachians. Well, we can see them now. They're at the surface now. We could go, for example, into what we call the Piedmont, and that's where we see all these metamorphic rocks. If you go to the Piedmont, which would be that part of the Appalachians, just to the east of the Blue Ridge, unfortunately, a lot of it goes under the coastal plain where we can't see it anymore. But the rocks that are exposed in the Piedmont, those are the metamorphic rocks that were down in that zone of subduction when those two pieces of Earth collided to each other. So we can now see them. It's obviously hundreds of millions of years later, but that would be an example of dynamo-thermal metamorphism. Now, since it covers a big area on the surface, some people would refer to that again as regional metamorphism. It's not a different kind of metamorphism, it's simply that it's exposed over an entire region like that. And for example, again, they would go in, and depending upon where you were relative to the actual collision site, there would be zones of different metamorphic minerals that you would be able to identify, indicating where you were relative to the collision site. So there's all kind of things these metamorphic people do to try to reconstruct a zone of subduction that existed 250 million years ago. And you see, that's what geology is all about, trying to figure out what it was like 250 million years ago. So that's the dynamothermal. Now, the hydrothermal is something different. Again, heat's in there. We're talking thermal here. But the hydro part, that's the chemically active fluid. That's where the chemically active fluid comes into play. Now, the chemically active fluid, it sounds pretty hairy, but what it is really hot water. But remember now, water is the universal solvent. It will dissolve more things than any other solvent known to chemists. Molten rock dissolves more than that, but that's another story. So anyway, here we have now hot water. Question. Where does the water come from? Well, let's go back for one thing to that zone of subduction. Now, down in the zone of subduction, we just talked about the dynamothermal, but there's also hydrothermal going on because there is water involved in the zone of subduction. Question, where does it come from? Well, there are a couple of sources. For one thing, here we have this oceanic lithosphere plate diving down into the zone of subduction, and right above it, of course, we've got the ocean. Now, what do you think the possibilities are of some of that oceanic water being drugged down into the mantle along with that descending plate? Well, I think it's probably pretty good. And so there's one source of water. I don't know how much that represents in volume, but I suspect it's probably appreciable. And remember now, in terms of chemistry, that's not pure water. That's water with a lot of stuff dissolved in it. That's why it's salty, you see. There's stuff dissolved in it. So here we have a chemical solution, if you will, being pumped down into this zone of subduction that can do some other things down there. Now, there are a couple of other sources of water that are also being taken down into the zone of subduction from the ocean. You'll have to take my word for this, but all over the world there's dust settling out on the ocean surface. These are just dust particles that are picked up as the wind blows across the land and it's hauled over the seas, and they fall out on the ocean surface. They fall to the ocean bottom. So if you were to go to the ocean bottom, chances are, rather than actually seeing the absolute surface of that oceanic basaltic crust, it probably would be covered with at least a little thin layer, relatively thin layer, of these sediments that fall through the ocean, just dust from above. Well, if you look at some of those sediments now, think about it, they're going to be drugged down into the zone of subduction along with that descending plate too. Now, if you look at some of the minerals, if you see a mineral and it's written, let's say, AB dot water, thinking a little of your chemistry now, AB dot water, that's a chemist's way of saying that there is water tied up in this mineral. Now, the dot implies that it's not very tightly held. Case in point, the mineral gypsum. We talked about gypsum. The formula for gypsum is calcium sulfate dot 2 waters. You could take gypsum home, put it in your oven in your kitchen, turn your oven up to maybe 450 degrees, and that's Fahrenheit now, and what would happen is that bond, that dot bond, would be broken, the water would be taken off, dehydrated, and what you'd have left behind is just calcium sulfate, which is anhydride. So you see, that the way a chemist has of saying the water's there, but it's not very tightly held. Well, there are minerals being drugged down into that zone of subduction that have formulas like that, those dot waters. But here's another one. Another way the chemist has of saying there's water in this structure of this particular material. Let's say you have a formula AB with a hydroxyl in it. Anytime you see a hydroxyl, that OH, that's another way of a chemist saying there's water in this structure. Because if you take things that have hydroxyls like that and you heat them up, you're going to have to do it to higher temperatures though, because that's more strongly held, you'll drive off water. Case in point. Take calcium hydroxide, CaOH twice. If you take calcium hydroxide, now this would take more than your home oven would do, but let's say you put it in a furnace and maybe heated it up to maybe 500 or 600 degrees centigrade. What would happen? It would dehydrate, and what you'd end up would be calcium oxide and water, 2 waters. In other words, the water would eventually come out there too. It took more energy to do it, but still it came out. So between those three, between water being drugged down, just seawater being drugged down along with the plate, and these two kinds of minerals that would provide water down in that hot zone, you do have water within that zone of subduction. And as a result, that water can then attack the rocks as they're being transformed. It can take things out of some of the rocks, put other things back. So now what's going to be the result? What the result is going to be that the metamorphic rock that's going to form is going to be not only mineralogically different from what you started with, but compositionally different. The elemental composition is going to be different. So now it gets a little bit more hairy, you see, a little bit more complicated. Now there's one other hydrothermal situation I'd like to describe, because this one has some economic value, I think. Picture, if you will, a mass of molten rock being injected into the part of the crust. I don't really care where it is. Let's say it's injected into this layer of sedimentary rocks that covers everything. Now it's going to sit there and cool off. Now, all molten rocks, all magmas contain water. Now, you have to take my word for it at the moment, but in another lecture, I think the next lecture, we're going to talk about volcanism. Whenever you see a volcano erupting, the big billowing cloud, of course, a lot of it's ash, I understand that, but a lot of that is just simply condensed water vapor or steam. The main gas evolved from all volcanic eruptions is water vapor. So all magmas contain water. Well, think about that now. Here's this magma, water's dissolved in the magma, kind of hard to visualize, but it is. And now what we're going to do, we're going to cool this magma down, and we're going to start precipitating out whatever minerals that magma is allowed to precipitate. In other words, again, whether it's felsic or mafic or whatever. But the point is, if you look at the minerals in Bowen's reaction series, or that crystallization series, and look for things that are dot waters, you won't find any. Okay, so you don't have to worry about those kind of minerals. Are there any minerals in the series of silicate minerals that have hydroxyls? Yeah, there are a few, but the hydroxyl, if you look at the entire formula, really doesn't seem to be very, very important. There are other things that are more abundant than hydroxyl. So the point is, some water is used to create minerals like the micas or like hornblende, but not much, which means that as these minerals start to precipitate out now, they're not needing to use that water. So the water in the magma becomes more and more concentrated. And pretty soon you're going to get to the point at the very end of crystallization when it's almost all solidified. What was once a molten rock mass with water dissolved in it is now going to be mainly just hot water with whatever's left dissolved in it. But that's the point. What's left? Well, let's think about that. What could be left? Maybe gold. Look at the minerals in Bowen's series. Do any of those silicate minerals require gold? No. How about silver? No. How about platinum? No. How about a lot of metals like that? No. You see, they don't need them. They don't want that stuff. So what happens? It's now in that solution at the very end. So we have this hydrothermal solution, we call it, just perhaps chock full of all these kinds of what we consider very valuable, rich, and expensive elements. Then what happens? At the very, very end, that stuff is shot out into the host rock, the stuff that's been contact metamorphosed, you see, and it's shot out there in cricks and crevices and like that, and all those things start precipitating out. And the result is perhaps a little vein of gold, a little vein of silver, deposits of metals that now are economically of value, and as a result, those are sites where we go to find that stuff. So note, one of the important things about this hydrothermal metamorphism is that as a result of it, we are creating, in many respects, a lot of metallic deposits of all kinds of things, molybdenum, you name it, that are being formed as a result of the end product of crystallization of magmas where these very rich and valuable things are concentrated in the final hydrothermal solution. It's all part of hydrothermal metamorphism. But again, note, then the metamorphic rocks we're talking about, now these things are different in composition from what we started off with. So anyway, you can get some feeling there, I hope, from just that little discussion of what the range of metamorphic conditions are and the kinds of different kind of metamorphic rocks you can find. It's very, very, very complicated. Now, the last thing I want to talk about actually has to do with how we describe metamorphic rocks. Metamorphic rocks are described as either being foliated or non-foliated. Now, here's the big difference between what foliation means. Foliation means that this rock contains platy minerals. Now, what's a platy mineral? Well, think back to our discussion of the silicate structures, those sheet structures where you arrange things, the silica tetrahedra, in sheets, and then sort of made sandwiches with the sandwich material being other cations, and then you stack them on top of each other to form things like mica and things like that. That would be a platy mineral, okay? Those are platy minerals. If you take a rock that has lots of platy minerals and they're all aligned with each other, just picture this now. Between those sheets is sort of weaker bonding, so you could break it between there. Remember? Mineral cleavage. So mineral cleavage, that's why you can take those books apart of mica. All right, so here we have a rock that has platy minerals in it. All of them are aligned, and so it would break along those weaknesses. And so that would be what we refer to as foliation. So foliation refers to the ability to break along these planes of weakness. Well, let's just show you the different kinds of foliation. And again, let me start off my old favorite, shale. All right, we take shale, and what shale is are clay minerals. And remember now, they are sheet silicates. So when that shale first formed, what happened is all those little silicate minerals fell down. They're all parallel to each other in the individual layers of the shale. And then what we're going to do now is we're going to metamorphose this thing. And here's what we're going to do. We're going to say just under pressure. Okay? So here we take this shale now, and we're going to set it under pressure. And under the new pressure now, those clay minerals aren't very stable, and what they're going to start doing is they're going to start changing, recrystallizing into, let's say, mica. Okay? Now here's the point. Let's say, for example, here was the pressure, your 2 fingers. And as these new platy minerals formed, what they're going to do, they're going to reorient themselves in such a way that they are stable under those new pressure conditions. So here's what I want you to picture in your mind. Take a coin, and what I want you to do is to hold this coin between your 2 fingers, like that, and you can hold it any way you want, but press on it as hard as you can, okay? Question, what would be the stable position, do you think? For example, if you took the coin and you put the coin like this, okay, and you're pressing on it, how stable do you think that would be? Just try it. You press on it harder and harder, pretty soon it's going to flip out. That's all there is to it. It's not a stable condition. On the other hand, if you took the coin and you turned it sideways like that, and remember now, your fingers are directly opposite each other, that's called non-rotational compression. Now you can push as hard as you want, and it will do anything because it's in a stable position. So note now, all these new platy minerals that are being created out of the clay minerals, now what they are, the micas, they're all rotating, getting in order, so they're all perpendicular to the forces that created them. Now we have, instead of clay minerals, now we have mica and quartz, all right? Well, it's a new rock. What do we call it? We call it slate. That's what slate is. Basically, slate is a metamorphosed shale. Now, the thing about that, we call that slaty cleavage. Why? Because if you take just a wedge of some kind of chisel, you can break that off into sheets, very uniform in thickness, very smooth surface. That's slaty cleavage. For example, back before the days of the white board and the green board and the orange board, we used to have blackboards. That was slate. Now, I think they actually sort of polished those surfaces to get them really fine. But I remember being on a field trip over in Wales and going into a quarry where they were actually making slates for roofs. And these guys were just sitting there with a chisel and hammer and splitting off these slabs that were perfectly uniform, about 1/4 of an inch thick, beautifully smooth on one side. That's what's characteristic of slaty cleavage. Now, if we squoze a little bit more, I love that word, squoze. Can I use that? Fair enough. If you squeeze a little bit more, now the mica is no longer stable. It's probably going to change to something else, maybe chloride, but other things are going to start happening. For example, there's going to start reactions now, and then they're going to be equidimensional crystals formed, not platy minerals, maybe things like garnet. And now, for example, in between these sheets now, there are going to be places, there are going to be garnets in here. So now if you try to split it, it'll split into layers all right, but they won't be uniform in thickness, and they'll be a little rougher and not quite as smooth. Well, we call that phylitic cleavage. Phylitic because the rock now is a phyllite. Note that a little bit change in composition. Now we have a phyllite. Now, if you keep the squeezing going on, pretty soon you start making more and more and more of those non-platy minerals, like, for example, garnets. And pretty soon, if you try to split it, it won't split in layers. What happens, it splits around the individual garnets, and you get flakes and things like that. Well, now we call this schistose cleavage because the rock is called a schist. The last of the kind of foliated rocks, and there's no cleavage involved here. I don't really know why it's called a foliated rock. It's called gneissic banding. The rock is called gneiss. Gneiss is the most abundant of all the metamorphic rocks. Now here's what it looks like. It's banded. Dark minerals, light minerals, dark minerals, light minerals. Now you tell me how the dark and light minerals separated from each other as a result of that metamorphism. I really don't know. But that's called gneissic banding. No, so those are the foliated rocks. Now the non-foliated, very simple. Non-foliated rocks would be rocks that have no platy minerals whatsoever. Case in point, a limestone. Let's say you take a limestone and now you're going to metamorphose it. What happens is it simply recrystallizes from the individual little crystals of calcium carbonate, whether they're individual crystals or maybe shell fragments, and they're going to recrystallize into new crystals. Shell fragments are gone now. You've eliminated all the fossils. They're gone. And what you end up with is a new rock where you have these relative uniform sized crystals of calcium carbonate all locked together. And the new rock, of course, no foliation whatsoever. And the new rock is called marble. That's what marble is. It's simply metamorphosed limestone. And the beauty of marble is you want a marble that's most uniform in texture. You don't want weakness, because if you're a sculptor and you start whacking away at this time to carve something, you don't want to run into a plane of weakness that's going to break and an arm will fall off or something like that. So anyway, that's marble. That would be a classic example then of a non-foliated rock. Okay, so much for metamorphic rocks. Next on to volcanoes.